Well, I rechecked here the kinematic of car-like robot. So actually, the problem is on the notation. Um, Actually, in here it states very clear that the inner and outer back wheels circle around the instantaneous center of rotation. So this implies that these VL and VR are linear velocity at the back wheel here. So the radius, this one for this one, the radius is r minus L over 2, and for this one, the radius would be r plus L over 2. That is correct. But the notation VL is here, VR is here. It's the same as notation here. That's why it's very confusing. Then it doesn't matter. Then just uh, use this VL and VR to be here. So in this case, the dry is on the back wheels, not the front wheel. Okay, yeah, need to be clear. And so this type of kinematic is especially appropriate to model larger vehicles. Okay, for this kinematic, and actually it can be simplified to be tricycle kinematics. Um, then we can average the angle alpha L and alpha R. Okay, average it. Yeah, it's kind of approximation, not really the exact averaging. So this alpha L and alpha R, it described by just one approximate average alpha. So as you can see in Samsung, it's like you take this one plus this one, and like this one cancel this one, but of course not. Of course not. We cannot cancel that in that way, but it looks just like that. That's why we can just have average, approximate average alpha like this. So it's kind of we can consider as one dry, like a tricycle here. This wheel here, this wheel, and this wheel is substituted by this wheel, something like that. Okay. All right then. So let's I continue to the second part of today's lecture. So during the next 1 hour, I will be covering the control of various wheel mobile robots. Control um, in the sense of having the robot to the reference position and with the reference orientation. Okay, like here you can see that the starting point of the robot is here, position is here, and orientation is minus pi, or pi is fine, and the goal is this position, and the orientation angle is this. Okay, so this one is pi because orientation is like this. So this control um, it is kind of we assume that we can control the actuator velocity. Okay, as long as we can we define the desired linear velocity v. Okay, I call it desired, omega desired. Once we can define this, we can definitely control the actuator motion to have this velocity and this angular velocity. Okay, so we make this assumption. Then for this lecture, the control is just to find a way that to find the trajectory or path and um, controlling parameter such that it can reach the goal. Okay, reach the goal mean the position of the robot, reach the reference position, the orientation of the robot, reach the reference orientation. Okay, this is the reference orientation, for example, like this. Okay, so first let's take a look at the orientation control. So we can analyze separately between orientation control and linear velocity control. So we denote E as the error of orientation. So yeah, this is our reference orientation at the goal. So at the goal, we want the robot to have orientation this way. Okay, this is goal at the goal, and the start. Yeah, at the initial position actually. Start maybe the orientation of the robot is like this, so the angle is like this. So this one is phi at 0, and phi at phi of t, it means maybe the robot is moving up to some point here, and at that point it has the orientation like this. So this one is called phi of t. Okay, yeah, at instant time t, something like this. So we define the error of orientation. Yeah, instantaneous error of orientation. And then let's take a look at the orientation control for differential drive. So we already have relationship phi dot equal to omega. And then we take omega as by this. It means a constant time this error, okay, this error, constant time this error. Then if we substitute omega into equation 3.1, we have the equation of phi dot only, right? So phi dot equal to k phi ref minus phi of t. Phi dot here also phi dot of t. So you can see that this is first order differential equation, and at the steady state we expect that phi of t tends to phi reference. Okay, yeah, from the property of first differential equation, I can say it in another word that phi reference is particular solution of this differential equation. And right, so here actually the desired angular velocity omega. So we compute desired angular velocity omega based on phi reference that we command and phi instantaneous orientation that we can measure. How can we measure this? So if we use a wheel encoder on each wheel, then we can compute, we can calculate the increment of the encoder. Okay, interpret it into radian. Okay, so this is obtained from measurement. This is command. So we calculate desired angular velocity based on this, and then we use the feedback control or using the control theory. Then we expect that the actual omega of the robot will be the same as desired, which means it satisfies this equation, then which means phi must approach to phi reference. That's the idea. You have a question at this point? This is very important if you want to implement it to a real system. Yes, to get the main idea first. Any question, Subun?
No question more.
Okay, that's good. It means you already understood. Okay. Well, so here we can just analyze in a different way that where this like a kind of filter, first order filter, described by closed loop transfer function. This one, first order. So we will look at the final value theorem for the step response. Step response phi rest has become 1 over s, and final value theorem, you have another factor s that cancel with the 1 over s of the step transfer function. Then limit s approach to 0, you get 1, which means this equal to this. Yeah, we can analyze in this way as well. Um, well, let's say we may want um, more property, like more feature of the response, not in the first order manner, but second order manner, because second order manner can allow have some overshoot, maybe can faster, and uh, we can get a certain settling time, something like that. So in that case, we might design a control law. Yeah, this is called control law, uh, to have second order in terms of phi, second order in terms of phi. So we choose, instead of choosing omega equal to yeah, proportional to the error, we choose uh, angular acceleration to be proportional to the error. Okay, so okay, so um, omega dot can be substituted by phi double dot. Then we have second order transfer function from the phi reference to the actual phi. Yeah, or we can say from the input of the feedback system of the closed loop to the output of the closed loop, right? Yeah, yeah. Here is the feedback actually, the control law of the feedback, because we measure the actual angle, and then we calculate the error based on that measure, and then we uh, generate different velocity or and different acceleration, something like that. So this is feedback. And okay, here we can see that, well, there is only, yeah, we can see that the poles of the closed loop is purely complex number, right? Pole is plus minus j square root of k. So we got the oscillation. Okay? We got the actual phi oscillating around the reference. Okay? Oscillate forward and back. It cannot reach. Okay, so it means the controller is not the best one yet. It's not appropriate yet. So we can choose a slightly different controller, which is much better, which is more appropriate for our system. So actually we just add another term, the damping term in order to reduce the oscillation, to decay the oscillation. So we need K2 here, and we substitute this equation into the equation of uh, phi dot equal to omega. Okay, so phi dot equal to omega dot. Okay, substitute this into this equation. Then we can have transfer function from the reference or the input of the feedback of the closed loop to the output of the closed loop, like this. And from final value theorem, we can see that when s approach to 0, I mean for the step response, s to 0, so this 0, this 0, k1 divided by k1 is 1. It implies that when time tend to infinity, we have this phi s, actual phi approach to the reference. And now we have second order, so the behavior of second order, like natural frequency, damping ratio, which relate the performance to like to have overshoot, how many percent, what is the rise time, settling time, something like that. Okay, so we can choose the right damping ratio and natural frequency omega n. Yeah, the right, I mean according to our desire. Is there any question? Munivan, do you have any question? Oh, I think I can hear you. Lihu, do you have any
No,
question?
no question.
Adrian?
It is okay.
Okay, good then. Um, okay, next let's see orientation control for the car-like robot. Um, so in here we have the relationship of orientation with the velocity of the, yeah, this is the rear wheel velocity. Okay, yeah, rear wheel velocity, but in the linear form. We can this one can be computed by omega of the rear wheel times the radius of the wheel. Okay, and alpha here is the steering angle. So actually in here the control variable are alpha and, well, let's say if we fix the angular velocity of the rear wheel, then the control variable is only alpha. Okay, then the controller must be chosen for alpha. So here for this equation, alpha is chosen to be proportional to the error of the orientation of the car. Then this alpha, so this is alpha desired actually if we consider it in the control theory, alpha desired. And okay, so I mean alpha desired for the control at the actuator parts. Let's say the steering wheel has another actuator motor to rotate it, to steer it. Okay, so we just command alpha d into the actuator and with the control hardware there, and then the actuator surely turn the angle alpha, the actual alpha, to be the same as alpha d. Okay, and then let's look at the response on the kinematics. Okay, because here we have the kinematic equation. If we choose alpha to be like this, and what happened to the actual orientation? Okay. So in this case, um, we do the approximation if the angle of alpha is small, which means uh, we don't steer too much. So actually for car, I think maybe at most around 45 degree. So actually the approximation here for small alpha, but the small meaning here not very small. Actually it can be to some extent like 30 degree or 40 degree. So the tangent of alpha for the small alpha can be approximated by this. Okay, so tan alpha is approximated to be alpha. Then we can have transfer function from closed loop input to closed loop output to be first order like this. Okay, so when time tend to infinity, we expect uh, as limit as tend to 0, then this just 1, which means this tend to this one. And again, if we want to have second order behavior of the response, then we choose alpha dot. It means we choose the controller for the velocity of the steering. Okay, and then we can have transfer function from closed loop input to closed loop output to be second order like this. Then we can choose k1 and k2 to satisfy our desire. Okay, now the second part of motion control, which is forward motion control. So like I mentioned earlier, we have orientation control and forward motion control. So here we are trying to control the linear velocity. Okay, and so what is the idea to control linear velocity? um, we have a start point here and we have a goal here. Yeah, linear velocity, it means the velocity on the trajectory. Okay, at this point linear velocity is supposed to be this, at this point linear velocity is supposed to be this, at this point linear velocity is supposed to be this. How about this point? Yeah, at this point what is the linear velocity? This is supposed to be this or what? So at this point we want it to stop, so it means linear velocity must be 0, is vector 0 here. So one idea to relate the linear velocity with the goal and the reference. Goal mean reference, but goal and instantaneous position and orientation. Oh no, sorry, instantaneous position. Yeah, the way to relate it is that while we choose the linear velocity, to be proportional to the distance from this point to the goal. It means if we are still far away from the goal, linear velocity should be very high, so we can go very fast. When it is close to the goal, the distance is small, then the linear velocity is also small. So when it arrives at the goal, the linear velocity must be zero. Okay, so this is how we choose control law. The basic idea to choose control law, which is to be proportional to the distance from the instantaneous position to the goal. Yeah, so this is the position, the distance, right? Delta x square plus delta y square, and put square root. And yeah, just to be cautious, if uh, the location of the robot is too far away from the goal, then the desired velocity here, the controller here, could be too large such that it may induce instability, or it may reach the limitation of the velocity of the robot itself. So um, yeah, especially the biggest problem is that too high velocity may induce instability. So it's important, advisable to introduce maximum velocity. Okay, and in practice, actually, it's a limitation based on the actuator limits. Okay, so the maximum velocity of the motor on the wheel will define the maximum velocity of the robot. And also another problem that may happen. So in practice, we need to be cautious. Um, yeah, due to imperfect model, imperfect parameter, and noise disturbance, then we can never get the portion exactly the same as a reference. So velocity v cannot be exactly zero. Then it implies that when the robot arrive around this point, it may it may drift back and forth or oscillate around here. Okay, of bouncing around here. So to remedy this problem, we can choose, like, if the distance of the robot to the reference point is small enough, close enough. Yeah, we can use some threshold value. Then we just command the velocity to be zero directly. Okay, we can remedy it by this method. And one more thing that we can consider is to smoothing the linear velocity, because for example, at the starting point, perhaps we don't want it to rise to the maximum velocity immediately, but if we want it to go smoothly. For example, so let me illustrate here. Let's say, because at the starting point, the distance from the robot to the goal is very far, then velocity calculated from the controller can be very large, but then we limit it to the maximum due to the limitation of the actuator. So let's say at the initial times, the linear velocity that we compute uh, from the controller to be start at maximum. So it looked like a step. Okay, when we start, then we put it into the maximum velocity like this. But I don't think this is preferable because any robot for the car as well, uh, we can't just make it uh, reach the speed at time zero to the maximum, right? Yeah, can make it reach the maximum speed at time zero. So we can consider. So actually, the dynamic itself of the car will make it not to be possible. But even so, we don't really know how the dynamic behave. So instead, we can deal around with the kinematic itself. That we should put a filter to smooth, okay, to smooth it, to smooth the desired velocity itself. Okay, the desired. Let's say this is desired. Um, to smooth it this way. Okay, so we can choose first order filter here. This one is uh, the desired velocity directly computed from controller. So yeah, DC means direct control. Um, V star is the filter velocity like this. So this one is this one is V star, and this blue one is V. Okay, then we combine all the idea above to have a good control of the robot. Okay, let's see one example. Write a control algorithm for a tricycle robot with a rear power pair of wheels to achieve the reference position H ref, Y ref. So it's the goal. 4 meter, 4 meter, H ref, Y ref. The vehicle is controlled with the front wheel steering. So we use the kinematic equation of front wheel steering, angle alpha. Uh, oops. Mm, rear power pair. Sorry, this one is rear power pair. Okay, rear power pair. It means the drive, the actuator is put on the rear vehicle. Yeah, but we control the steering angle alpha. Okay, be careful. So be careful to choose the kinematic equation correctly. Okay, and by the rear wheel velocity VR. Okay, we control the rear wheel velocity as well. The distance between the front wheel axis and the rear wheel axis is d. Okay, so this is distance d. Initial position h0, y0, and phi0 is this. So here is the start. T equals 0 is here. T tend to infinity is expected to be we expect the robot to be here. So here is 1 meter, 0, and angle minus pi. Yes, orientation. And the control algorithm should consider vehicle constraint V max only 0.8 meter per second and alpha max 45 degree. Yeah, the steering angle 45 degree. Then um, the example it asks us to write a control algorithm and test it on simulation of the vehicle kinematics using Euler integration method. So it's okay. Euler integration method, just right hand side time sampling time, okay, and plus the previous state, state in the previous time step. So it's very easy. So I think we can directly see the code. First, choose sampling time, uh, create duration from 0 to 30 seconds, incremented by the sample time 0.03 second. Distance, okay. Reference 4 meter, 4 meter for each ref and y ref. Q, the instantaneous position, state actually. So it's h of t, y of t, and phi of t. Yeah, Q. And then we make the loop. Make the loop. In it means we try to every se- uh, every instant. I mean, yeah, of course we cannot have a supercomputer that calculate everything in at instant. Every sample time ts, we want the microcontroller to compute the controller, okay, and then we uh, input it into the kinematic equation to calculate the actual position of the robot, okay. So in this code we just need to write the code for every sample time, and then we use the loop in order to run from 0 to 30 seconds. So the loop here is loop on the time. File reference can be computed, uh, yeah, using the this one is arctong 2. Arctong 2 is to return the angle to be sure that it can give the angle on the four quadrant. So this one is arctong of y, y ref minus y ref minus y of t. No, y of 0, I think. Yeah, at initial time y of t is y0 actually. So looked y res, yeah, because we use q1 q of 1 q of 2, not q of k, so it's not instantaneous, but actually y at time 0 h ref minus h at time 0. So arctong 2 of this, it means arctong of this divided by this, but the angle must return in the four quadrant. If we don't use arctong 2, the angle return only the first quadrant. So this we must be very careful at this point, otherwise it may show the wrong answer. All right, and q reference. So we want q to approach to q reference. We have hy coordinate reference and this, so it means h ref, y ref, and phi ref. Okay, and here we can calculate the error between the instantaneous state q and the q ref. Okay, and then we can compute the control law. V equal to k times the distance. Okay, distance based on this error. This error is in terms of vector. Okay, it's error vector. Yes. So error vector from the instantaneous t to the goal. and then the distance is the norm of the error. So it's, yeah, this error or distance from the current position to the goal. Get same thing, eh? Sometimes I say distance, sometimes I say error because it does not reach the goal yet. So the distance itself is the error. So this is the norm. So velocity, linear velocity is proportional to the error, and alpha is proportional to the error of the orientation, right? Well, and then yeah, this one is k phi ref minus phi t. So k is 0.2. For this one, k is 0.3. And then physical constraint, we limit the angle alpha. We cannot steer alpha to as much as possible, right? Alpha must be at maximum 45 degree. So if absolute alpha greater than pi over 4, then alpha is just pi over 4 times its sine. Okay, and then we limit velocity if absolute velocity, uh, yeah, this is actually this one is always positive. We don't need even to use, uh, we don't need to use absolute, but in anyway, no problem. So we limit the value up to this only point h. And here is the kinematics. Once we have controller, we feed it into the kinematic equation. So dq means the, okay, dq means h dot, y dot, and phi dot on global frame. So make sure that you choose the kinematic equation correctly. Okay, you choose kinematic equation for to find the velocity in the global frame. And now we can consider it later. Um, then using Euler method for the integration, we just use the right hand side times sample time and plus q at the previous time step. Previous time step here, it means when the once a certain value k, it compute to have value q, and then it go to the next loop. Then this q actually for the current, this q mean for the current loop, this q is from the previous loop. Okay, so this is kind of k plus 1, this one is kind of k, like qk plus 1 equal to qk plus the right hand side times the sample time. So this is Euler integration method.
Sir,
Yeah,
can you remind me of how you choose K, like 0.3 and 0.2? I'm not sure I understand.
yeah, actually this is a tuning parameter. uh, there's no exact way. Oh, well, for, well, if you look at the feedback here, because here just first order, um yeah, like here. So it depends, like what is this, yeah, like this is first order, right? So for step response it's be like this. So from here like how, um like at what the settling time, let's say at 2%, at 2% of error here, you want at 2%, so the time at 2% is called settling time. So we can um choose k such that you can have a desired settling time. You got the idea? Um, so I can rewrite this one like d over vk here as tau. Tau is the time constant, right? Time constant. So at one time constant tau, you only get 63%, right? And at two time constant, you get like 70 or 80 something. I don't remember exactly. And then maybe, well, at 2%, you need to choose, for example, like 4 tau. I don't remember exactly. So from here, um, 4 tau, and 4 tau you want it to be like 3 seconds, for example. Okay, 3 seconds. Then you have d over vk equal to 3. Then you can find k equal to something. All right, you got the idea?
Yes, yes, yes. Thank you.
Yeah. And if you want to compute the exact number here, because we consider in terms of percentage, so I just put here is 1, and the curve here actually is just 1 minus e to the minus t. Tau t. Tau, oh, sorry, t over tau. Okay. So based on this, you can play around with the value of tau, and then you plot to see like how many seconds it reached 2% or something like that. You can do some simulation to check, and then you make the decision that, well, I want the settling time is 5 seconds or 3 seconds or 4 seconds, and then you can choose k. So this is a, if you want to follow the analytical method to choose k, and the method is just to tune it. You choose one value and you do simulation, and then you consider the appropriateness. I mean, is it possible that this robot can reach the goal at 3 seconds? Let's say the initial of the distance from initial position to the goal is like 50 meters, and you want the settling time only 3 seconds, then it may not be possible, right? Well, so but anyway, the larger the value k, the shorter the sample time, the settling time. So of course, first we want short time, the settling time to be short, to be small. We try with big number, but if it or incur instability, or yeah, instability can come from numerical error. Instability can come from the limitation of the actuator. No, because we already set the limitation. Um, Instability can occur due to the uncertainty of parameter or something like that when you deal with the real hardware. But anyway, I just give you the idea that you can try to tune it using big value and then reduce to smaller. If for simulation you start from big, but for experiment you should start from small. Yeah, for implementation, yeah, you start from small. It's it's okay to have it take longer time to reach the goal, but not to have it move in a chaotic motion and break down the hardware or something like that. Okay. um all right, I think that's all for today's class. So I will see you next week for the last lecture, I guess.
Yes.
Next week will be the last lecture. Yeah,
Okay.
the last class. Yeah.